we're going into continuous. So, continuous random variables, we discussed yesterday. They have an infinite sample space, essentially. There's no way to list every possible value my variable can take on. With that, then, it starts to cause a lot of problems in terms of calculating probabilities. So when we think about that, a continuous random variable can take on any value. If you have a range of values that are acceptable, your continuous random variable can take anything in between those values. Okay? So that causes some major issues with probabilities. Can anybody just figure out why? Why would that be an issue for calculating probabilities? Think about in a discrete case. So let's say our random variable x, if we list out the values, so let's say we could have anything from 0 to 5. Okay? So if I was able to list out my sample space, how do I calculate probability? Over what? Over how many there are, right? So we take each individual, so how many times or how many ways 0 can happen over the total number of ways it can happen, right? Now in a discrete set, that sample space is countable. So we have a finite number of values in our sample space. But in a continuous random variable, we would have an infinite sample space. So if I tried to calculate the probability of one single value, what would happen? Yeah, you'd be essentially taking 1 divided by infinity. There's an infinite number of possibilities for our sample space. And 1 divided by infinity doesn't work, right? So what this means is that any one single value in my sample space cannot have an associated probability. So for instance, I could not find the probability that my random variable takes the value 2 exactly. Because no matter how many different ways my variable can take the value 2, I would still be dividing by infinity, an infinite sample space. So in discrete variables, we could calculate the probability that x was equal to 2. We just took the number of ways 2 could happen, divided by the total number, and we were done. It doesn't work that way with continuous. Now, the other thing that does, if we can't find the value of one specific, if we can't find the probability of one specific value, then when we start looking at ranges of values, greater than, less than, greater than or equal to, less than or equal to, they all become identical. If I want the probability that x is greater than or equal to 3, that is going to be the exact same probability as if x was greater than 3. So yesterday we had to be real careful. If I said less than or equal to, that meant I was including the value itself. So if I said x is greater than or equal to 3, I would have to include 3, 4, 5, 6, up to whatever. If I said x was simply greater than 3, then I excluded 3. So I started with 4, 5, 6, up to whatever. But we just got done talking about the fact that one single value can't have an associated probability with it. So whether I include 3 or not include 3, I'm going to end up with the same probability, because if I don't include 3, I'm starting so close to where 3 is on the one side or the other that it's like I'm not even excluding it in the first place. There's no probability above 3 itself. Does everyone understand that? So when you're looking at the problem with continuous random variables, greater than or equal to, greater than, less than or equal to, less than, doesn't matter. They're all calculated the same. Okay, so in this case, with continuous random variables, we don't care if we have the or equal to or not, because the probability is going to stay the same regardless. Is everyone okay with that idea? Because it's kind of an important one.
Can you go over that again?
Okay? So, we said that an actual value itself cannot have an associated probability, right? So the probability that x equals 2 doesn't exist. If I took a number divided by infinity, what essentially am I going to get? If I take something and divide it by a huge number, you're going to get an extremely tiny number, right? In fact, if I was going to infinity, I would essentially get 0. So the probability that x equals 2 in a continuous case is the same as saying 0. It doesn't have a probability for that one specific value. So in a problem, when they give you greater than or equal to or greater than, you don't have to worry about the or equal to because it's like 0 anyway. It's like it doesn't exist at 3, so we can only go greater than anyway. Does that make sense?
Yeah.
How do you know if it's continuous?
You have to think about the scenario. So, yeah, like if you're looking at rolling a die, so you have a finite sample space there. You have a 1, 2, 3, 4, 5, or 6, right? So I can list the different values. But if I were to say you're great on a test, so you could have 0 to 100%, right? But technically you could have anything between 0 and 100%. So you could score a 26.7, you could score a 98.7432, or so on, depending on the number of points that were in there. So in that case, we can't list our sample space, which means there's an infinite number of possibilities from 0 to 100. Anything, any number that you could possibly conceive of between 0 and 100 would be a possibility. So that's one of the things yesterday we kind of discussed, and today I wanted to reiterate, is when you're looking at a scenario, it's imperative you know whether you're working with discrete or continuous. And that's just something you have to take on a case-by-case scenario. Okay? All right. Now, with continuous random variables, if we couldn't calculate single probabilities, normally we would just be out of luck. There's nothing we can do probability-wise. However, we are able to treat continuous random variables the same way we treated density curves back in Chapter 2. Namely, when we have a normally distributed variable, we can use our normal distribution calculations to calculate a probability over a given range. So we still cannot calculate the probability of an exact value. It can't be done with a continuous variable. But we can calculate the probability that our variable is greater than or less than or in between certain values. And we're going to do it the same way we did back in Chapter 2 with our normal distributions. Okay? So if you have a continuous random variable, basically what you're going to be working with is a normal distribution problem. Okay? So, an example. The heights of young women closely follow the normal distribution, which has a mean of 64 inches and a standard deviation of 2.7 inches. So with the normal distribution, remember, it had two values we had to know. We had to know mean. Where's the center? We had to know standard deviation. So what's the spread? Okay? So they've given us both of those. Now, how we apply that to what we're discussing right now with random variables. If we were to choose a young woman at random from our population and measure her height, okay? We could call her height y. You can define the variable in anything. Since we're talking height, you could have just as easily called it h, whatever you want, so capital Y. Now, if we were to continue to just randomly select women, so we just selected one woman after another, and continued to measure their heights every time. Well, if I were to do that enough, my distribution, my values that I'm collecting, should start to follow the normal distribution we expect for women's heights. So when we take on our random variable, we define it as the height of a randomly selected woman from our population. If we do it over and over and over again, the distribution we collect should follow the distribution we know to be true for the population. Does everyone get that? So we can take our random variable now and describe it with our normal distribution. So if we want to know the probability that a chosen woman is between 68 and 70 inches tall. So if I were to go out into the population and select a woman at random, I want the probability that when I measure her height, it's between 68 and 70 inches. Okay? So if we think about this visually, remember our normal distributions have that bell shape. Okay, so they're a smooth curve. We know that our mean is at 64, so 64 should be right in the middle, right at the hump. And then a standard deviation of 2.7. So if I reach 2.7 in each direction, that's one standard deviation. If I reach 5.4 above or below, that'd be two standard deviations, and so forth. So our question is, how do we calculate the area under the curve? So remember with normal distributions, probabilities were calculated by finding area under the curve, right? So we want the area between 68 and 70 underneath our normal curve. So if we were to leave it in these terms, we'd have to use a pretty high order of mathematics here. We'd have to figure out the equation of our curve. We'd have to use some calculus to integrate and find area underneath. We don't do that, okay? Instead, we have a way to convert 68 and 70 into a system where all of our areas have already been calculated for us. So what do I need to do with my 68 and my 70 here? Standardize. What does it mean to standardize? Find the z-score. How do we find z-scores? Use an equation. Now the table takes z-scores as input, gives you the probability as output. Anybody remember? All right, we'll bring it up here in a second. Okay, I just want to see how much of chapter 2 we kind of remember. I'm glad we got standardized and we got z-score. Everyone kind of remember those? Okay. So, when we want to do one of these problems, first thing we need to do is establish what we're actually trying to find. So that's what we just got done discussing. We want to find the probability that our random variable y is between 68 and 70 inches. Okay, so this is just a recreation of the graph we had on the last screen. But what they told us was that we have a normally distributed variable. So we know that the mean height is 64 inches, standard deviation is 2.7 inches. We want to get to the point where we can find the probability that a woman chosen at random is between 68 and 70. Okay, so we just said we have to standardize. We can't work with 68 and 70 without higher level math. So we need to get to z-scores, which allow us to use a table where they've already done the higher level math for us. Okay, so when we go to perform our calculations, and with these, you guys need to make sure you're showing me your work. Okay, if you show no work and you end up making a little mistake somewhere, you lose lots of points as opposed to maybe half or 1 point because you added or subtracted wrong, or you did order of operations incorrectly. So show everything on these problems. So the first step is to find the z-score. Now, before you write these down, let's write the general formula first. To calculate a z-score, you take the value of your variable. Okay? Now, for our purposes, I'm just going to give it a generic x. But it could be y. Like in our case, we should be using y because that's our variable. If we called our variable h, we call it lowercase h, whatever you need. Okay? I'm going to use just a generic variable. So x minus the mean divided by standard deviation. Okay? Know this formula. You have to know it. Memorize it. Okay? Z-score is equal to the value minus the mean divided by the standard deviation. So on these problems, they are always going to give you your mean and standard deviation. The only thing you would have to calculate is either z and use it, or use a z-score to get back to x. So these are the only two you'll ever have to solve for, are x and z. Everything else should be given in the problem.
So we do it for 68 and 7, both?
Yes.
Okay.
So now, since we want between two values, between 68 and 70, we need to calculate a z-score for 68, so that's the problem here. Take 68 minus the mean, 64, divided by 2.7. Remember, z-scores go to two decimal places every time. So our z-score is 1.48. So that's going to be our lower bound. Okay? For our upper bound, we need to calculate the z-score for 70. So for that, we do the same process. 70 minus the mean, 64, divided by standard deviation, 2.7. We get a z-score of 2.22. So now, we have the two z-scores in question. So we can go to our table and use it to find our probabilities now. So when we have a z-score, we look it up on the table. So we go to 1.4 on the left column, so make sure you're on the positive side. So you go 1.4 on the left, find that, and then follow it all the way across until you're under the 0.08 column. Point what? 0.9306? Everybody find that? Okay. Now we need to do the same thing for 2.22. So go to 2.2 on the left column, go across to the 0.02 column. 0.9868. Now let's talk about this first. When you looked this up, so when you looked up 1.48, what does this 0.9306 actually mean?
The left to the right, the area underneath.
That's how much area is to the left of that point, right? So 93% of our area is left of 1.48. Same thing with the 98.68. 98.68% of all my values are left of 2.22. Okay, so that table tells you everything left. Now, since we had two values to concern ourselves with, we wanted the area in between. So if I know the area of each to the left, what do I need to do with these to find just the area in between? Subtract them. So take the large minus the small. So take your 0.9868 minus your 0.9306. 0.0562. Okay. So this would be so we have about 5.62%, right? So 0.0562, that's giving you the percentage in decimal form. So the probability, so what we'd have to say here, because remember we have to have an interpretation, we can't just give a number. What does it mean? We would say that the probability that a randomly selected woman is between 68 and 70 would be about 5.62%.
Leave it as a decimal or 1%?
It really doesn't matter. It's easier to word as a percentage, but you could leave it as a decimal. Whenever I do it, I give the answer as a decimal, and then when I interpret it, I always put it in percent. It's just easier to word. Okay. So anything to that effect, where you're saying if there's a 5, or so you could also reword it this way. There's about a 5.62% chance that a woman selected at random is between 68 and 70 inches tall. Okay? So every one of these problems needs to have the final answer, the final probability, and an interpretation. What does that probability mean in context? Okay with that?
Well, like if it, didn't include the like, less than or equal to, greater than or equal to, or just less than or equal, or less than or greater than, you do the same thing.
Yep. So, if I were looking at this, and I ask you for this value. So we just got done calculating the probability that 68 was less than or equal to y, was less than or equal to 70. So if I changed it up, and I said, well, what's the probability that y is strictly between 68 and 70? So the women can't be exactly 68 or 70. What's my new probability going to be? The exact same thing. Okay, so regardless of whether we have the or equal to or not, the probability will be the same. Everyone okay with that? Okay. Now, real quick then, I just want to go over this a little bit more here because I know it's been a while since we've seen this stuff. What if I had asked the question, what's the probability that a woman chosen at random is less than 68 inches tall? We would calculate just for 60, so for 68. Did I say 60? I meant 68. Did I say 68? Okay. So the probability that she's less than 68 inches tall. Okay? So we would do the exact same process, but we'd only have to worry about 68 inches tall. It's the only thing we're concerned with. So we calculate the z-score, 1.48. We said we wanted the probability that she's less than, right? So we would simply take the exact value from the table. So 0.9306 would mean there's a 93.06% chance that a woman selected at random would be less than 68 inches tall. Okay? If I had said, what's the probability that a woman selected at random was greater than 70 inches tall? Then we'd go to 70, we'd get the z-score, and then subtract from 1. So once we take our z-score and find our probability, so 0.9868, subtract it from 1, which would give us 0.0132. So about a 1.3% chance that a woman selected at random is more, or taller than 70 inches. Okay? So less than, remember you just take the value from the table, call it good. Greater than, 1 minus the value from the table, and then in between, like we just did, is subtracting the two values from each other. Okay with that? All right. Hopefully, since we've already gone through this once, hopefully these normal distribution calculations go a little bit better the second time around. Okay? So, here are the problems I want you to try out for tomorrow. Same stipulation as yesterday's assignment. You need to have started at least a couple of these problems by tomorrow. Okay? So, you got 10 minutes here. Plenty of time to get a couple questions done. So if you're still working on yesterday's, if you still have questions from yesterday's assignment, make sure you get those answered. I'm just going to circulate around, answer questions as we go. If you are done with that assignment and you want to start working on this one, you can do that. Okay? So, grab a book if you need to. Get out your book if you need to. But I need you to work on finishing yesterday's or starting today's. But you are working on one of the two things.
Can I see my quiz anytime? Or is that? Have to wait.
Hold on one second.